Hello Physics 1 students, and welcome to your Lab 11 Prelab video. Today we're going to be discussing collisions. So the important things that we're going to discuss about collisions are momentum and kinetic energy. So in a collision, momentum is always conserved. However, energy may or may not be conserved depending on what type of collision we're talking about. So if energy is conserved, that means it's an elastic collision. If energy is not conserved, that means that the collision is inelastic. Okay? And you can have just a regular inelastic collision, or you can have a perfectly inelastic collision. In both cases, energy is lost, but in a perfectly inelastic collision, your two masses or your two colliding objects are going to fuse as one and move together as one after the collision takes place. I left a link down here that's just a nice little summary about collisions. If you want to watch it on your own time, feel free to do that. But I'm going to keep going with the slides. So momentum, as I mentioned, it's always conserved, and unfortunately, I know we just used rho as our symbol for density, but rho is also the symbol that is recycled for momentum. And so rho, or momentum, is equal to mass times velocity. Okay, so in terms of always being conserved, what that means is that our initial momentum is always going to equal our final momentum, or rho I is equal to rho F. And one other thing that I wanted to mention too is that this is velocity, so we do care about the direction. So when you are calculating momentum, you need to either define the direction as positive as the problem tells you, or if it's not given, make sure that you're defining a positive and a negative direction and assigning that direction correctly when you're calculating momentum. All right, so on the next slide, I have just an example collision sketched out here. So you can see up on the top, this is initial, so this is before the collision takes place. And down here on the bottom is final, so this is after the collision takes place. So we have mass 1 headed in the positive direction at a positive velocity v1 initial. And then we have mass 2 heading in the opposite direction, so heading in the negative direction at v2 initial. Okay, then after the collision, we can see that both masses rebound off of one another and they change direction, right? So now mass 1 is heading in the negative direction at V1 final, and mass 2 is heading in the positive direction at V2 final. So as we mentioned on the previous slide, the initial momentum always equals the final momentum. So that means the momentum before is equal to the momentum after. Or in terms of masses and velocities, we have m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. So, and as I mentioned on the previous slide, make sure that you're paying attention to your signs, right? Because velocity is a vector. So if we're defining the right as positive, that means v2 initial and v1 final are negative quantities. All right, moving on to our other quantity, which is kinetic energy. As I mentioned, this is not always conserved, but the way that you calculate kinetic energy is always the same, and it'll be 1/2 times the mass times the velocity squared. So you can probably see here, even though we're using velocity, the direction doesn't really matter this time, right? Because we're going to square the term. So if we have a negative quantity, we're going to end up with a positive quantity. If we have a positive quantity, we continue to have a positive quantity. So momentum is really where you need to pay attention to your signs. Kinetic energy, it doesn't matter as much. So as you can see here, the initial kinetic energy does not always equal final kinetic energy. But if it does, that means that it's an elastic collision, right? And you can see that here. Kinetic energy before is equal to the kinetic energy after. So if you have an elastic collision, like I'm sure you were taught in chemistry, that gases undergo perfectly elastic collisions with their containers, that this would be the case, right? However, in the real world, most of the time what you're going to observe is that there is no such thing as a perfectly elastic collision. If you get in a car accident, if you're playing football and you run into somebody, if you kick a soccer ball, all of those collisions are going to be inelastic because some energy is lost as heat, sound, friction, etc. Right? So what this means in terms of KE initial and KE final is KE initial is going to be greater than KE final because some energy is being lost. All right, this next slide should be all review. These are the concepts we were just talking about. So if we look at elastic and inelastic collisions mathematically, we know that both momentum and kinetic energy would be conserved in an elastic collision, but in an inelastic collision, momentum would be conserved, but kinetic energy would not be conserved. So if you look down here with the elastic collision, you can see that KE initial is equal to KE final. So the reason that I didn't include momentum here is because in both cases, momentum is conserved, right? And we already talked about what that would look like. The momentum before is equal to the momentum after, which means that M1V1 initial plus M2V2 initial is equal to M1V1 final plus M2V2 final, right? We already went over that, so I'm just highlighting the differences here. So if you have an elastic collision, remember that means that you don't lose any energy, so the energy before is equal to the energy after. So that means 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared is equal to 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Right? We have the same illustration here. M1 is initially traveling with V1 initial. M2 is initially traveling with V2 initial. Then after the collision, they hit each other and they both rebound. So M1 is traveling at V1 final after the collision, and then M2 is traveling at V2 final after the collision, right? So you can see all of those terms in this equation here. Now, if you have an inelastic collision, that means your kinetic energy before is not equal to your kinetic energy after. You're going to lose some energy, right? So that means if you were to set up your equation the same way we have here, these two quantities would not be equivalent, right? Because we're losing some energy. And then I mentioned this already, but for kinetic energy, it doesn't matter if you're paying attention to your direction, right? Because you're going to be squaring your velocity quantities, right? But if you do need to calculate momentum, do make sure that you're being careful and you're paying attention to the directions of the velocities and you're getting the signs right. All right, so this is that special type of inelastic collision that I mentioned in the beginning, a perfectly inelastic collision. So, of course, it's inelastic, so that means we're going to lose some energy. Momentum is always conserved, so it is. And then masses are going to fuse after the collision. So what that looks like is you have M1 traveling with V1 initial in the positive direction. Then you have M2 traveling at V2 initial in the negative direction. After the collision takes place, both M1 and M2 fuse together and they travel at one mass at one final velocity. Okay, so in terms of what the momentum would look like, well, we know it's conserved, so the momentum before is equal to the momentum after. That means M1 V1 initial plus M2 V2 initial is equal to M1 plus M2 times V final. And then in terms of kinetic energy, we know that these two quantities are not going to be equivalent because it's an inelastic collision, so we are losing energy, right? So that means 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared is not going to be equal to 1/2 times M1 plus M2 times V final squared. Now, on either side of the equation, you can see how you would calculate initial kinetic energy and calculate final kinetic energy. But remember, these quantities will not be equivalent. All right, so now we're going to look at a couple real-world collisions. They're both, of course, inelastic collisions. The first two are just going to be regular inelastic collisions, and then the last one is going to be a perfectly inelastic collision. Actually, in here, the second collision is going to have a perfectly inelastic collision as well, and I will point that out as the video is going. So this is our first video, which illustrates at least several inelastic collisions in a row, and I'm going to go ahead and get the video started. All right, so there we saw an inelastic collision with this guy's foot, an inelastic collision with this pole here and then an inelastic collision with this guy's face, right? So we'll watch that one more time. All right, collision 1, 2, and 3, right? So we had the inelastic collision between the guy's foot and the soccer ball, then an inelastic collision between the pole and the soccer ball, and an inelastic collision between the guy's face and the soccer ball. Now, how do we know that it's inelastic? Well, we, for one, could hear that there was a sound, so we know some energy got dissipated as sound, and I think we can be pretty certain that in that last collision, there was definitely some deformation of the goalie's face. All right, so this is one of my favorites. This is kind of a classic video. So what we're going to see here is actually an inelastic collision followed by a perfectly inelastic collision. So let's see. All right, so let's watch that one more time. So when the guy collides with the wall, that was an inelastic collision. Now when the guy collides with the floor, that's a perfectly inelastic collision, right? Because him and the floor are one unit now, right? So let's watch one more time, and we'll see the inelastic followed by the perfectly inelastic collision. All right. So there you have it, an inelastic collision followed by a perfectly inelastic collision. Now let's watch our third and final video, which is just a perfectly inelastic collision. So you can see as this girl cartwheels, she collides with the floor, and now her and the floor move as one, or don't move as one in this case. So let's watch that one more time. Perfectly inelastic collision. There you have it. All right, so that's it for the videos. One meme before we move on to the pre-lab practice problems. All right, so pre-lab practice problems number 11. So we have 9 practice problems. Let's go ahead and get started. All right, so if you read the prompt at the top of the pre-lab practice problems, it says there are 2 gliders moving from opposite directions. They collide on an air track. The masses of the gliders are 0.3 kilograms and 0.7 kilograms. So you can see I have mass 1, this is 0.3 kilograms, and mass 2 is 0.7 kilograms. Before the collision, the speeds of the gliders are 0.3 meters per second and 0.45 meters per second. So this guy, before he collides, is going to be 0.3 meters per second. This guy is going to be a negative 0.45 meters per second for reasons that I'm about to mention. After the collision, the first glider rebounds with a speed of 0.4 meters per second. So rebounds with a speed of negative 0.4 meters per second. Don't worry, I'm going to tell you why it's negative in the next sentence. We're going to assume that the first glider is initially moving in a positive direction. So there you go. We know that going to the right, as I've drawn my picture, that's going to be positive because our first glider is initially moving in a positive direction. So that means anything going to the left is going to be negative. So V2 initial and V1 final, right? Because they say it rebounds, so it's going to change direction. So now it's moving in the negative direction. However, I didn't put anything here for V2 final because they don't tell us anything about what mass 2 is doing after the collision. We're going to have to calculate that in a later problem. Okay, so pre-lab practice problem number 1 says what is the momentum of the first glider before the collision? So the momentum of the first glider before the collision, so rho 1 initial is equal to m1 v1 initial, right? And that's equal to 0.3 kilograms times 0.3 meters per second, and we get 0.09 kilogram meters per second. Now there is no standard unit for momentum, so you can see here I have kilogram meters per second, and the only guidance that I can really give you as far as converting goes is look at what your multiple choice answers are in, what units they have, and try and match those units when you're calculating. You'll notice for the pre-lab practice problems, all the answers in parentheses are in kilogram meters per second, so that's what we're going to be keeping our units in, kilogram meters per second. But I did want to let you know that there is no standard unit like there is for newtons, right? For newtons, it's always kilogram meters per second squared, but the unit for momentum can change. All right, moving on to problem number 2. What is the momentum of the second glider before the collision? Okay, so the momentum of the second glider before the collision is equal to m2 v2 initial, so 0.7 kilograms times negative 0.45 meters per second. So we have a negative 0.32 kilogram meters per second. Number 3, what is the total momentum of the system before the collision? Okay, so the total momentum of the system before the collision, so that's rho initial, that's going to be equal to rho 1 initial plus rho 2 initial, right? Because those are the only objects that are involved in this collision. So we sum them up, and that gives us the total momentum, right? And specifically before the collision. Okay, so we know that the momentum before the collision for mass 1 was 0.09 kilogram meters per second, and we know for mass 2 it was negative 0.32 kilogram meters per second. So when we add these together, we get a negative 0.23 kilogram meters per second, which we know should also be the final momentum, right? Because momentum is always conserved. All right. Problem number 4. What is the momentum of the first glider after the collision? So now we want the momentum of the first glider after the collision. So that's going to be m1 times v1 final. So that's 0.3 kilograms, mass 1 has not changed after the collision, times negative 0.4 meters per second. So we get that the momentum of the first glider after the collision is negative 0.12 kilogram meters per second. All right, number 5 is a little bit longer. Number 5 says apply the conservation of linear momentum to calculate the speed of the second glider after the collision. So first of all, we know that the momentum before is equal to the momentum after, right? That's applying the conservation of linear momentum. Okay, so that means both of these, momentum before and momentum after, are equal to negative 0.23 kilogram meters per second. All right, so that's a thing that we know. Another thing that we know is that the final momentum is equal to m1 v1 final plus m2 v2 final, right? So if we substitute those values in here, right, we have the final momentum is equal to negative 0.23 kilogram meters per second. And that's equal to m1 v1 final, or negative 0.12 kilogram meters per second, right? That's what we calculated right here. Okay, m1 v1 final. All right, then we know that m2 v2 final, well, we know m2 is equal to 0.7 kilograms, and then we have one equation and one unknown where we're solving for v2 final, right? Yes, we do want speed, but if we take the absolute value of whatever we get for velocity, that will give us speed, okay? So the next thing that we're going to do is we're going to add a positive 0.12 kilogram meters per second to each side, right? So then we end up getting negative 0.11 kilogram meters per second is equal to 0.7 kilograms times V2 final. Now, in order to get V2 final by itself, we want to divide both sides by 0.7 kilograms. So we do that, and we get that V2 final is equal to a negative 0.16 meters per second. Now, because we want speed, we want to take the absolute value of our velocity value, which is negative, right? So when we take the absolute value, we get a positive 0.16 meters per second. Now, if you are looking at the answer key that's on the Prelab practice problem sheet and you see that this is 0.15, I cannot wrap my head around how it was rounded to 0.15. If you calculate this and you round at the end, you get 0.16 meters per second. But you can rest assured that if you take the quiz, you will not have an answer that would be 0.16 and 0.15 that you would have to choose between. So it should be 0.16, but the question sheet somehow got rounded. Maybe they rounded earlier when they were doing it, so it got rounded to 0.15. But if you do round at the end, you will get 0.16. All right, so problem number 6. Did the second glider rebound after the collision? All right, so we can see this is the second glider, right? And it was initially traveling to the left, right, at 0.45 meters per second. Then after the collision takes place, it is still going to the left, but now at a diminished speed or velocity of negative 0.16 meters per second. All right, so if we think about this, we know that rebound means change direction, so no, M2 did not rebound after the collision. It continued moving in its initial direction. So that should be pretty straightforward. Problem number 7. What is the kinetic energy of the system before the collision? All right, so we know that the initial kinetic energy is equal to 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. So when we plug in our values, we have 1/2 m1, which is 0.3 kilograms, times v1 initial, which is 0.3 meters per second. We're going to square that term. Then we're going to add it to 1/2 times m2, which is 0.7 kilograms, times v2 initial, which is negative 0.45 meters per second, and we're going to square that term. Now, when we multiply out and add these up, we get that this is equal to 0.084 joules. All right, so moving on to number 8. What is the kinetic energy of the system after the collision? So KE final is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So we get that the kinetic energy after the collision is equal to 1/2 times m1, which is 0.3 kilograms, times v1 final squared, which v1 final is negative 0.4 meters per second. We add that to 1/2 times m2, which we know is 0.7 kilograms, times v2 final squared. We know v2 final is negative 0.16 meters per second. So when we multiply out and we add up these values, we end up getting that KE final is equal to 0.033 joules. Yes, I know that the answer sheet says 0.032, but we are using this correctly rounded value, which gives us 0.033. All right, last but not least, practice problem number 9. Is this an elastic collision? Justify your answer. So an elastic collision would mean that KE initial is equal to KE final, but 0.084, which is what we calculated for KE initial, that is not equal to 0.033 joules, which is what we calculated for KE final. So because this collision results in a loss of kinetic energy by the system, this is not an elastic collision. All right, so that's it for the pre-lab practice problems. If you want to stay tuned, I am going to quickly review circular motion because, as you know from experience, there will be 5 questions pertaining to circular motion on quiz 11. All right, so just to review circular motion, what we talked about last week, well, we know that centripetal force, or F subscript C, that is the net force on an object traveling in a circular path. Now, without this net force, the object would not travel in a circular path, right? We know from Newton's first law, it wants to go in a straight line, but it's being acted upon by a force, which is keeping it traveling in a circular path. So in terms of this drawing here, we would have some mass, right? And I think the simplest example is just a mass on a string, right? So the tension in the string is what's providing the centripetal force, right? And it's traveling in a circle. So we could be swinging the mass around above our heads maybe, okay? So it's traveling in a circular path. If there were no tension in that string, that mass would cease to move in a circular path and it would fly out tangent to the circle, right? We know that if we were to release this mass that we're swinging over our heads at v linear, right, or our linear speed. Now, of course, because we have a force, that means we also must have an acceleration. So the centripetal acceleration is this vector here, right? This is going to be radial to the circle, and as we already established, v linear, our linear speed, is tangent to the circle. Now, because we are moving in a circle, we will typically be given in our problems a radius, right? Now, remember, you want to convert this radius to meters because we are talking about forces, which do have SI units, right? Newtons are kilogram meters per second squared. So a similar caution for your mass, if it's not already in kilograms, make sure that you convert it to kilograms because Newtons are kilogram meters per second squared. Now, along with that, if you're given the period, and if that's not in seconds, it usually is, but if that's not in seconds, you want to make sure that you convert the period to seconds. And then just for review, because we haven't mentioned it already, the period is the time it takes the mass to travel around the circle once, right? So it's the amount of time it takes for this mass to make one revolution. Now, your important equations for centripetal force are going to be, of course, for centripetal force, which is, as it's defined, the net force on an object traveling in a circular path. Centripetal force is going to be equal to your mass in kilograms times your centripetal acceleration in meters per second squared, right? So that at the end, we get something in Newton, right, which is kilogram meters per second squared. Now for angular speed, which is typically represented as omega, this little w here, that's going to be 2 pi over the period, and the units are radians per second. Linear speed, typically depicted with a lowercase v. This is going to be omega times r, or if you want to write the whole thing out, it would be 2 pi r over the period, and the units, as speed units typically are meters per second. And then last but not least, centripetal acceleration. Now, yes, you can calculate centripetal acceleration up here, right, by dividing the centripetal force by the mass, but that would mean you have to have the centripetal force. And in the problems, you're not always given that, okay? So if you're given things like the radius of your circle, your period, your mass, then you would probably be calculating it this way. So your centripetal acceleration is your linear speed squared divided by the radius, and of course it's an acceleration, so the units are meters per second squared. All right, so that's it for the review of centripetal force and circular motion. Hopefully you found this helpful, and best of luck on quiz 11.